Now I'm going to talk about how you might measure distance and velocity from acceleration data and some of the pitfalls involved. So imagine we've got a device attached to a shank, a x-axis is pointing upwards, the y-axis backwards, and the z-axis into the page. Now the shank coordinate system is defined by the line connecting the malleoli, that's medial lateral, the ankle joint centre connecting the knee joint centre, that gives you the vertical axis of the shank. And then you've got the AP, which is found by the cross product of these two axes. Now imagine the accelerometer gives you this 9.8100 at rest. The 9.81 you can see in the x-axis corresponds to gravity, so that's telling us that the device is aligned vertically. You can also get some magnetometer data out of the device, and this might, after it's been normalized, give you something like 0, -1, 0 to be very simple, and this -1 is in the y, but you can see that y is pointing backwards, so you would interpret this as that the north is actually the inverse, the opposite direction from y. So north is in this case equal to the AB axis, or forward. So we've got a very simple system here. Now, sometime later you read the accelerometers and you read the following: 9.81, 0.5, 0. So now the device is not at rest. The first thing you have to do is subtract the gravity component. That was there at rest, and obviously we are not accelerating in that direction, that is just due to gravity. So acceleration is 0.5. Actually, we'll make it minus 0.5 to make this example simpler. Now, minus 0.5 is being measured in the y-axis, but because y is opposite to the anterior-posterior axis and also north, we know that the person is accelerating 0.5 meters per second squared forwards. So if you want to find out how fast they're going, if you want to find out how fast they're going, you have to know how long they've been accelerating. So they started from rest, and we'll say they've been going for 10 seconds. So the final velocity equals the initial velocity plus acceleration times time, equals 0.5 times 10 equals 5 meters per second. Now if you want to know how far they travelled in that time, distance equals VIT plus half AT squared. Now you see the problem is, as we measure distance, the times term is being squared, And acceleration, small errors in acceleration can have a bigger and bigger effect on the calculated distance. So in this case, it would be 0 plus 0.5 times 0.5 times 10 squared equals 25 meters. So perhaps this would happen if you're sitting in the car and we're accelerating slowly from the lights. But usually we don't use accelerometers to measure distance because there's too much room for compounding errors through integration. It's better to use GPS or some other device better suited to measuring distances.